Okay, this is graph theory wrap up. We're going to finish off Lefort chapter 14 and thus graph theory in the book and go on from there. We're going to do a little grab bag of topics representing weighted graphs, Floyd's algorithm, big O for graphs, and the famous classic traveling salesman problem very briefly. Representing weighted graphs, surprise, there are two approaches. We can use an array, in which case we call it an adjacency matrix. We can use a linked structure, we call it an adjacency list. This should sound very familiar to you, very much like the unweighted graph, and indeed it's very much like it, but it's got a few little kinks to it. So here's an example. Here's a simple graph, but this time it has weights on the edges, right? And if we put them into an adjacency matrix, we put the weights into the graph instead of putting zeros and ones. And if we have a bidirectional edge, we have to put the weight in for both directions. The diagonal shows the relationship from the vertex to itself, just like it did with the unweighted ones. Some put zeros on the diagonal. I've left it blank. You really shouldn't end up accessing it, so it doesn't particularly matter. Here's an adjacency list. It's very much like the unweighted adjacency list, except we have to take the node that represents the edge in the linked list, and we have to add a weight to it. We can't put the weights into the vertex because some vertexes have more than one edge. A, for example, has 3 edges. Even if we had some sort of way of storing multiple values in the vertex, we would then have to keep track of which weight went with which edge. That's difficult. So we add the weight into the edge. Okay. How do we implement these? Well, in adjacency matrix, we use a two-dimensional array, probably of int, possibly of double, or maybe even of short if we're trying to save a little space. If we're doing a list, same as the unweighted, except you'll notice in class node, we've added a weight, right? It happens to be an int here, could have been a double, possibly a short. Okay, so that's implementing your weighted graphs. That's your how you implement them. A couple of possibilities. Next, Floyd's algorithm. This is a version of Warshall's algorithm, but it's for weighted graphs. Warshall's only works with unweighted graphs. We use ones and zeros there. It's designed to work with an adjacency matrix, as with Warshall. Typical implementation, you use a triple nested loop. We've got a loop that goes through all the rows. We got a loop within that loop that goes through all the columns. And if we find a value in the column, then we go back for the column for that row, and we go down that column. And so that's our triple nested with NIF. Very similar to Warshall's, except one little kink here. As we find new roots and we generate a new value, we have to be sure that we don't replace a shorter path with a new but longer path. So there's an additional if statement. We'll see an example of that in a second. Okay, so this is the example out of Lefort. It's a very simple little graph, right? We can follow it pretty easily. It happens to be directional. That'll just give us a little less to do in the example. And we represent the adjacency matrix as on the right. And you can see I've put the weights into the various rows and columns to have a representation of the graph. All very straightforward. Applying the algorithm, we can go through row A. It's empty, so there are no actions. We can go through row B. As we go through row B, we find things, but the B column is empty, so again, we're not going to take any action. We get down to row C, and we find that we have the condition that C goes to A. There's a value there, a value of 30. So we're going to look into column C. We're going to go down to column C, and sure enough, at the very end, we find a value of 20. So we look at column C, and we find that D goes to C, and we found that C goes to A, and so we can add into our table that D goes to A. Of course, since we're going indirectly, we're going, right, we have to add the two values. So C goes to A, and D goes to C. So we add the 30 and the 20, and we get 50 for the total root using the two edges. If you go back and you look at the graph that we originally had, the little drawn version, this becomes pretty obvious. Now, row D, we go through row D, and D goes to A, and B goes to D. So B goes to D, which goes to C, which goes to A. And if we add those up, those values up, we get a 30, a 20, and a 10. That adds up to 60. Or we can go directly from B to A, that's fewer edges, but the weight's bigger. So we want the smaller weight. So we'll replace the 70 that we had a minute ago with a 60, okay? Finally, row D, we find that D goes to C and B goes to D, so B goes to C. We have to sum those two. We add the 10 to the 20, we get 30, and we plug the 30 in there, and we're now finished, okay? So that's Floyd's, the weighted version of Warshall. Okay, big O. As you know in this course, big O is important. The big O for graphs are all on LaFour, page 710, and we'll just run through them real quick. Adjacency matrix requires looping through rows and columns for the most part. If that's the case, which it usually is, that means that we have a big O of the number of vertices squared, right? Okay, that should make sense. If we have an unweighted adjacency list, most of the things we do with that, since we're doing the list rather than the matrix, how often do we have to do things? Well, the number of vertices plus the number of edges, right? Which of those is smaller, V plus E or V squared? Well, it depends on how many edges you have, right? This gets back to our idea of sparseness. If it's sparse, we go with the list. If it's not sparse, we go with the matrix, okay? Weighted graph. With the weighted graph, a minimal spanning tree, we have this big O, edges plus vertices to the log of V. Dijkstra algorithm, very similar. We're basically threading our way through both structures, okay? Warshalls. Warshalls, we have our nested loops, triple nested loop. As you might guess, a triple nested loop gives us a big O of number of vertices raised to the third, V cubed. That's true for both Warshalls and Floyd's. If you remember what we said at the beginning of the course, we're not really happy with algorithms that are a square term. Algorithms with a cube term are, of course, considerably worse. So in general, we're pretty unhappy with these. The redeeming feature is that we can run them once and then we can look up the result, and looking up the result is very fast. So if we expect to change our graph only fairly rarely, and we expect to look up values in it frequently, then it might well be worth building the table with one of these algorithms, even though they're a bit slow, so that we can do the lookups. Okay, we're going to finish by talking about a classic problem. This is one of our problems with our shortened course this time due to the pandemic, and that is we're not going to be able to spend as much time on classic problems in general. And I normally spend an entire lecture on traveling salesman problem. We're not going to do that. We're just going to take a couple of minutes, but hopefully it'll get you to start thinking about some things. So the traveling salesman problem, it's a classic problem. A traveling salesman wishes to make a tour where he leaves from his home and he visits each of his customers and he returns home. That should be pretty straightforward. That seems like a reasonable thing to do. He wishes to minimize the cost of doing it. That cost may be in terms of the number of miles traveled. It may be in terms of the amount of time it takes. If he's buying tickets to get places, like maybe plane tickets to get to different cities, it may be based on the cost of the plane tickets. But whatever it is, we're going to minimize the weights. That is, we're going to minimize the cost, whether the cost is expressed in dollars or miles or hours, okay? In which order should he visit the customers? Does it matter? Actually, it does matter quite a bit. We want to pick the best order, and it turns out that's not so simple. This is a simple problem I found, a simple graph I found for this problem. It's selected fairly carefully to give us an interesting result. So in which order should you visit the customers? Let's assume he lives at A, so he's going to start at A, he's going to finish at A. How do we pick this? Well, we could say, let's try a greedy approach. That's worked for a number of cases. It seems reasonable. If we do a greedy approach, right, we'll go from A to B, and so from A, we pick the shortest edge that takes us to some place that's not visited. That would be 2, that would be B. That's a greedy choice. We go to B. Once we get to B, well, we don't want to go back to A. We've already visited there. So we want to go someplace that we haven't visited from B, and we could either go to D or C. And we're going to pick the smaller of the two, right? Because that's a greedy approach. That's 4, that puts us at C. And then we can either go to E or we can go to D. We haven't visited either of them. Greedy approach, we'll pick going to E first. So we go to E, and then once we're in E, we've got to get to D. Yeah, because we haven't visited D yet. So we go from E to D, but that's a little expensive. That's 10. And then once we're at D, we need to get back to A. Our path from D back to A is 12. So we go A, B, C, E, D, A, and that's 2 plus 4 plus 2 plus 10 plus 12. So that's a total distance of 30. Okay, and that's not too bad. That's not too bad. It got a little funky there once we left C, but actually, really, once we got to E, we realized we had almost painted ourselves into a corner. But still, we got out of it with 30. Can we do better? Actually, we can, and this is the rub. We can do better if we go from A to B, from B to C, from C. Now here, the greedy approach would be to go to E because that's 2 instead of 3, but D's better connected. So we go from C to D, and we go from D to E, and now we only have to get back to A from E, which is much shorter. And so that gives us 2 plus 4 plus 3 plus 10 plus 5. That gives us a total of 24, right, which is noticeably less than 30. And so what can we surmise? Well, for a traveling salesman problem, greedy is not an optimal approach. It doesn't seem unreasonable. It doesn't give you terrible values, but it's not optimal. And normally I spend a whole lecture looking at how the traveling salesman problem's been used, things like that. It's very interesting, but we're a little short on time. So we'll leave it here with the fact that no, greedy is not optimal. Well, what does that mean for the bigger picture? So if greedy is not optimal, then how do we find the optimal solution to the traveling salesman problem? Well, we have to try each possible combination. So from A, we have to say, well, what if I go to B? What if I go to E? What if I go to D? What if I go to... We have to try all that. We have to try all the possibilities. Now, once we pick one, then there are fewer possibilities because we know we only need to visit it once. So what we get is a big O of V factorial, and that means the number of vertices to a factorial. So in the case of 5, that would be 120 different combinations that we have to try. For a V of 12, I just picked 12 because it seemed reasonably small. You can see you get this huge problem of needing to try over 479 million combinations. So factorials go up very quickly, even worse than squares, and it makes it very expensive. You can say, well, this is a nice problem, but who really cares? Well, it turns out that lots of problems map onto the traveling salesperson. Give you an example, these days we have lots of packages being delivered to people by people like UPS and FedEx. Well, when the FedEx guy or the UPS guy sets out for the day, they got a bunch of packages to deliver on that route. Where should they go first? Where should they go second? Where should they go third? It's a traveling salesman problem. At the end of the day, they bring the truck back to the garage or back to their home if they're allowed to keep it their home. But they come back to their starting point. They would like to have an optimal solution. They would love that, and they don't have that. And there are a lot of other cases where if we can solve the traveling salesman problem, we could do great things. So these are called intractable big O's. Once you get anything above O squared, a few O cubes like the Warshalls, we kind of grit our teeth and we put up with that. But as we get bigger than that, the numbers just go up too quickly, right? So if we want a traveling salesperson solution, just saying we'll try all the possible combinations, oh, it's not good. It's not good at all. We're going to poke at this just a little bit more a little bit later, but for right now, we're going to call this the end of our time in graph theory, and we're going to close out chapter 14.